Thank you very much for the opportunity to speak here. I'm particularly happy as a person who is interested in gauge theory to be staying at Weil lane, since Weil was the first person who talked about gauge symmetry. And indeed, the purpose of this talk is to advertise the idea that some concepts and techniques from gauge theory and more broadly analysis can be used to tell us something about invariance of symplectic manifolds. So let's say we have a symplectic manifold X, and all my manifolds will be closed and without boundary. And of course, a well-known problem is, in some sense, we want to be able to count pseudo-holomorphic curves in X. So to be a little bit more precise, we choose some almost complex structure J on X, which is compatible with a given symplectic form. Let's say we choose a homology class in X. And we may or may not fix the genus and consider the moduli space. So typically, this is denoted by M, say A, G, X, J. And I will put a little star here to be consistent with the standard symplectic notation. And this is simply the moduli space of J holomorphic curves in X, representing this given homology class and of genus G. So when I put a star here, I mean that I really care about images of J holomorphic curves rather than maps. And this is a well-studied object. In particular, it has an expected dimension given by the Riemann-Roch formula. So this problem of counting holomorphic curves is particularly interesting when the dimension of your manifold is 6. And this is the case I want to focus on today, in which case the expected dimension of this moduli space is given by a simple formula. It's 2 times the pairing of the first-gen class of X with this homology class A. So in particular, it does not depend on the genus. And in fact, I want to focus today on the case of so-called Calabi-Yau classes. So I assume here that my class A is so that this number is 0. I will say a little bit more about other cases. This is the most interesting case. So if the expected dimension of this moduli space is 0, you might hope that you can just count elements of this moduli space and get some sort of symplectic invariant of your manifold. But of course, there are 2 well-known problems with this, so maybe difficulties of this theory. Well, the first one is transversality. I know that the expected dimension is 0, but this modular space could be, in fact, very singular, could be something which is, for example, higher dimension, because my equation for a J homomorphic curve is not transverse. And finally, there's the problem of degenerations or compactness, that even though you are interested in images of J homomorphic maps in actual geometric curves in your manifold, the space of curves is typically not compact because these curves can degenerate to some sort of singular objects. And depending on what degenerations you allow, you will arrive at different theories of curve counting. And just to illustrate, so of course this subject originates from algebraic geometry, from people like Schubert and Grassmann, who were interested in projective manifolds and counting curves passing through some constraints of given degree. And just to illustrate that in algebraic geometry, these difficulties are highly non-trivial, I want to mention the Clemens conjecture. I'm not going to write it down because it's not very relevant to this talk, but I just want to state it, that it asserts that for a generic quintic threefold, so if you choose generically your coefficients of your polynomial, there are only finitely many rational curves of a given degree in that quintic threefold. So already and this is an open conjecture. I think it's only known up to degree 7, and it's a very hard conjecture. So already for genus 0, you see that there are some. First of all, you want to show that generically your curves form a zero-dimensional modular space. That's the problem of transversality. And second, that the number of these curves is finite. That's the question of degenerations. But in symplectic geometry, at least the first problem is a little bit more tractable. And that's something that leads to Gromovwitten theory. Namely, you can show that for a generic choice of J, this actually is a zero-dimensional manifold. But it is typically not compact. So what Gromov tells us to do is to embed this space in a larger space, the so-called modular space of stable maps. So what you do here, you consider these curves as maps up to reparametrization, and you allow also maps from singular domains. And in particular, since you now consider your curves as maps, you have to allow certain pathological objects in this modular space. So what I mean by pathological, I mean something that doesn't really have much geometric meaning. For example, you can imagine that you have a single genus 0 curve inside your X, nice embedded curve, and you can always consider a map, which is an element of your modular space of stable maps. Namely, you take any curve of higher genus here, and you consider this singular Riemann surface, and a map which is an embedding of this component, and simply a constant map taking values in some point here. And these maps always exist in your modular space, and moreover, they form a higher dimensional component of the modular space because you're allowed to vary the complex structure on this component, and you are allowed to vary this point. So this component of this modular space is never zero-dimensional. This is something that sometimes people call a ghost map, because it's a map, but somehow geometrically it's not there. So you see this interesting phenomenon that even if you started with a single embedded genus 0 curve in X, it produces all these maps for any genus, and it produces contributions, non-trivial contributions to the Gromovwitten invariance of any genus, even though it's just an object of genus 0. So that leads to so in some sense, you can make sense of counting points in this modular space, and that's what defines the Gromovwitten invariant, which is a rational number because you count multiple covers with rational multiplicity. So this is, of course, a very beautiful theory, but in some sense, there are all these objects here which are hard to understand geometrically. So it's natural to ask maybe a general question. Are there, I put it in quotation mark, more geometric ways of counting? So in particular, some other ways of counting curves for which you don't see these infinitely many contributions from ghosts. And also, ideally, you would want to have some integer numbers. Just like in classical enumerative geometry, you want to actually count some geometric curves passing through constraints. And, well, let me mention two instances in which the answer to this question is yes. So if the dimension of X is 4, then there is something called the Taub's Gromov invariant, which essentially counts embedded J-holomorphic curves, but with some weights on them. And maybe I'll talk a little more about this later. But also there are some invariants that come from algebraic geometry. So maybe this is A and B. If X is a projective Calabi-Yau threefold, so projective threefold whose with C1 equal to 0, then there are all sorts of invariants coming from sheaf theory. So the general term is Donaldson-Thomas theories. There is also a version called the Panther-Thomas theory. And essentially, the point of these theories is to think of curves as ideal sheaves. And then to use deformation theory of sheaves to consider appropriate modular spaces and extract integer invariants. So this theory gives you some kind of invariant in every homology class and for every integer n. And this is actually an integer, which in fact can be promoted to some kind of homology group. So it can be categorified using the theory of perverse sheaves. And there is a famous conjecture which says that these DT invariants are equivalent to Gromovwitten invariants. And somehow, what I'm going to talk about is some sort of quest for finding a symplectic interpretation of these Donaldson-Thomas invariants. Clearly, we cannot use the theory of coherent sheaves because there is no such theory on symplectic manifolds as far as I know. So we have to think of something else. So that's sort of the motivation for what I'm going to talk about, but actually, in fact, I will mostly talk about this side of the theory.
Sorry, a question?
Yes.
So the tau Gromovwitten invariant, that's also an integer?
Yes. It's some sort of, it's a power series with integer coefficients. So,
and then X is a threefold?
It's a complex threefold. So it's a complex manifold of dimension 3 with trivial canonical bundle.
So it's not in CP3? Sorry.
Oh yes, of course, yes. I think it's in CPN, and I meant to say threefold. It's maybe that's what I wanted. First something. Thank you. Yeah, of course, it would make sense. Right. Actually, there's a version of this theory that also works. In fact, for any complex. So for any projective threefold, it doesn't have to be Calabi-Yau, but the theory is particularly good for Calabi-Yaus. And somehow that's the most interesting part of the theory. So the theorem I want to state, let's see, maybe here. Everything I'm talking about today is joint work with Thomas Walpurski. And the main theorem I want to state is the following. It says something about this question of actually counting geometric embedded curves. So let's say that X is a symplectic manifold of dimension 6, and the homology class A satisfies the condition that it pairs with the first-gen class to 0. So we are in the situation I assume there. The first part of the theorem says that for a generic J, and by that I mean an almost complex structure on X, which is compatible with the given symplectic form, there exists finitely many, at most finitely many embedded J-holomorphic curves in X representing the given class A. And when I say finitely many, I really mean doesn't matter what genus. So no matter what genus. And by what I mean by J-holomorphic curve, I mean just the image of a J-holomorphic map. And the second part of the theorem says that in the special case, if A is a primitive class, and primitive means that it's not of the form K times B for k greater than 1 and B in integer homology group, then actually you can count these curves, and that's a symplectic invariant. So a signed count of these curves does not depend on J. So that gives you some sort of invariant, n a g x omega, which is an integer. And in particular, by the first part of the statement, we see that n a g x omega is 0 for sufficiently large g. So for g large. Because in the first part of the theorem, there are only finitely many curves, no matter what genus. So for some large genus, this number would be 0. So let me make some remarks about this statement. Are there any questions about the statement of the theorem? So let me make some remarks. So I should say that, of course, the most interesting case is always when A is actually not a primitive class, because then that's where all the trouble is with multiple covers. So the first part of the statement says that, nevertheless, for J generic, you can have finitely many isolated curves. You can define a signed count of them, but typically it won't be an invariant. And this is related to something which is called superrigidity. So let's say, what do I want to say? So for a non-primitive, this theorem, the proof, uses the fact that the generic J is so-called superrigid. Which was recently proved by Chris Wendell. In fact, what do I want to say? So I didn't define what superrigid means, but it's some kind of special property of J's which has to do with multiple covers. So if you want this to have this theorem, if say A is divisible by at most D, and you want to have the theorem hold, you have to know that a generic J is D-rigid, where D-rigid has something to do with the deformation theory of default multiple covers. So if you don't like superrigidity, you can just set A being primitive, and then you don't need that. Maybe I should also ask, there's some earlier work by F. Tekhari. So I'll be happy to answer questions about this, but I don't want to talk too much about this superrigidity. It's a very exciting result.
He proved it in dimension 6?
In any dimension. So you have to state properly what superrigid means in other dimensions. In dimension 6, when C1 is 0, it's nice because every modular space of 0 dimension. So it's of visual dimension 0. If you have some modular space which is of high dimension, then of course the curves are not even rigid because you can deform them. So there is a statement that makes sense in any dimension. Maybe I should. Greater. In 4 you can say something, but it's a separate story, I think. Yeah.
And when you say this, you mean theorem?
The theorem A was the one. Yeah. Yeah. Yes. For primitive classes, you just need normal rigidity. So another comment I want to make, there's this number which gives you the dimension of the modular space. So if this number is negative, then you can show that generically there are no holomorphic curves in in the class A, so that's a boring case. Another interesting case when this number is positive, well, then the modular space is positive dimensional, and instead of counting curves, you want to count curves that pass through certain cycles. And you can do that, and there is an analog, so there exists an analog of the theorem in this case. But in fact, and then you don't have to assume anything primitive because you can just rule out multiple covers for index reasons. So this case is somehow much easier than the Calabi-Yau case. So there is an analog of the theorem, but since it's easier, I won't be stating it. And I should mention that for A primitive, or satisfying the positive, so these are called the Fanon classes. So the A primitive or satisfying this inequality, there's earlier work of Zinger who defined these invariants AG. But his proof that these numbers are invariants uses Gromovwitten theory. So there is a non-trivial statement that Gromovwitten invariants are invariants. And using that, you can extract certain integers numbers from Gromovwitten invariants. And then because Gromovwitten invariants are invariants, then so are these NAG. What we do here is slightly different. We show that these numbers are invariant directly by studying what happens to the modular space when we vary J. But these invariants are not new because of this work. And maybe for those, I mean, if you're used to these things, you just look at it and like, well, this is just Gromov compactness in some sense. So maybe I should say that 1 does not follow from Gromov's compactness. Precisely because Gromov's compactness deals with J-holomorphic maps. And to talk about the modular space of J-holomorphic maps, you have to fix the genus. And we don't want to do that. So rather than using Gromov's compactness for maps, you have to talk about Gromov's compactness for currents, and then use some regularity for J-holomorphic currents, including work of Professor Delelis here. So I will talk a little bit about this later. OK. So I will talk a little bit about the.
Can I ask a question about what you just said? So Taubes has an analogous statement in dimension 4. Is this thing you're saying about Gromov compactness for currents how a generalization of that?
Yes. Yes. But in fact, in dimension 4, I mean, Taubes does something similar. But in dimension, well, in dimension 4, just if you insist, for example, on counting curves of index 0, right, then somehow index is related to the genus. So you cannot have an arbitrary genus if you fix a homology class and you insist on having like some index. Dimension 3 is really the only dimension where, if you have index 0 and some fixed homology class, you could possibly have infinitely many genera. But actually, Taubes, because he talks about disconnected curves and currents, he actually does something similar. And he was the first to have this result on the regularity of J-homomorphic currents in dimension 4, which is somewhat special because of the intersection theory.
Can I also ask, did Zinger know these were integers?
Yes. Yes. I will say something about this, yeah. This is related to the Gopak-Marvafa conjecture, which I will now talk about this. So when I said that it's an interesting question to find invariants which are maybe more geometric, there is a conjecture that there exist such invariants, and these are called the Gopak-Marvafa invariants. So Gopak-Marvafa had this paper on string theory where they considered something called BPS states, which is not something mathematically defined. These are some kind of states in string theory, and the point of these states is that they should be localized along J-holomorphic curves. And based on that, they had this prediction that so this is all for threefolds. So there should exist some integer invariants called BPS AG x omega. These are all integers. Some sort of count of BPS states, whatever that is. And moreover, they produce a formula which should relate these invariants to the Gromovwitten invariants. And so there is a universal formula relating BPS to Gromovwitten. So I mean, maybe I'll write down this formula because I won't use it, but just from looking at it, you can see that something interesting is going on. So you put all the Gromovwitten invariants in this formal power series in formal variables q and u, and this power series should be equal to some other power series given by the BPS numbers. Maybe some I think there is a 2 here. So there should be a universal formula which relates these invariants. And you see something interesting, namely that BPS invariants in a class A, let's say A is primitive. BPS invariants in a class A, because there is this Ka here and I sum over all Ks, will have contributions to Gromovwitten invariants for class Ka, for any K. So even if you have a single, if you imagine that you have a single primitive rational curve, for example, and all other BPS invariants are 0, if you believe that BPS counts some sort of embedded curves, then still that single invariant gives you a contribution to all higher genus and higher homology class Gromovwitten invariants. So that's something similar to what I explained at the beginning, that a geometric curve will have all these infinitely many contributions to Gromovwitten invariants. So in that sense, BPS is expected to be something a little bit more geometric related to the existence of, to counting just embedded curves. And that's something you can already see from this formula, although of course this is a very mysterious factor which is related to some integrals over the modular spaces of multiple covers. Okay, so of course it's a question, how do you actually define these numbers? And there are many ways people try to do this. Some use Donaldson-Thomas theories, so there are some proposals for these numbers, but then actually they don't know how to prove this formula. So then you can restate the conjecture. And an alternative way is just to say, well, you can define BPS by this formula because this is an invertible power. It's some combinatorial formula, you can invert it, so you can actually express BPS as rational combinations of Gromovwitten invariants, which are also rational. So then you can restate this problem of defining BPS as a conjecture. So define BPS by the Gopag-Moravaffa formula. Then what you want to show is that BPS AG is an integer, which is not obvious from the formula, because if you invert this formula, you would just write it as some kind of rational function, rational combination of Gromovwitten invariants. And then secondly, what they also predicted is that BPS, so maybe x, BPS of x AG should be 0 for G large. Meaning that if you give me a symplectic manifold and a homology class, there is some maximal G for which these invariants tell you something, and for higher genus, they are all 0. And the first part of the conjecture was actually proved recently. So 1 was proved by Ionel Parker, but 2 is open. The point is that, oops, sorry. The proof of Ionel Parker, it's a very beautiful proof. You start with some collection of curves, and you don't really know what is their contribution to the Gromovwitten invariant, but you know that you can deform the almost complex structure in the neighborhood of each j to some standard j, for which you know that the local version of this formula holds. And then you just have to study what happens when you do this deformation. But when they do this, they cannot avoid the situation that you have some concentration of curves. So you have some, say, nice embedded primitive curve, but there could be infinitely many curves of, say, higher genus or higher multiplicity, which converge to that curve. So they cannot exclude this situation. And if you have infinitely many of these curves, then a priori you could have infinitely many contributions, so you don't get this sort of finiteness. It could be, in fact, much worse. You could have a sequence like that, and this curve itself could be also the limit of infinitely many. And this one could be also the limit. So it's like there's this old poem by Jonathan Swift about fleas having smaller fleas, and the smaller fleas have smaller fleas, and it just never ends. So it's actually quite remarkable that they prove the theorem, and despite this, so it's a very beautiful proof. So in some sense, our theorem 1 says that in some situations, this situation cannot happen. So how is it related to this Gopa-Kumar-Vafa conjecture? So Zinger proved that if A is primitive, then the BPS AG is equal to this N AG, which I wrote over there. So as a corollary, we get the first instance of this finiteness conjecture. So 2 holds for primitive classes. So this is a corollary of this work of Zinger together with our theorem. And in fact, there is a similar story for classes A, which satisfy this positivity condition. So here, as I said, there is an analog of our theorem for these Fano classes. Then you have to put some constraints, and then you also get some numbers. And there is an analog of the Gopa-Kumar-Vafa formula. And you also have a vanishing result like that. So of course, the next step would be to try to prove 2 for an arbitrary class. And this is related to some sort of finding an analog of this for classes that are divisible by some numbers. So what this equality tells you that you can actually define a BPS number by simply counting curves if the class A is primitive. But as I mentioned, if your class is not primitive, you wouldn't expect that a naive count like that, even though according to the theorem you can actually write it down, you cannot expect that a naive count like that would be an invariant. So towards the end of the talk, maybe I'll state some conjectures about this. Okay.
Is it a lot of work to show that Zinger's NAGs agree with your NAGs, or is it fairly immediate?
It's not immediate. It uses various things. It uses the fact that if your curves are isolated and the contribution to the Gromovwitten invariant is some sort of integral over the modular space of multiple covers, and then you actually have to compute that, which was done by Pandaripand and Brian. But that, yeah. So this was proved by Zinger. So essentially, he studies that problem. Right. So what we do, which is different from what Zinger does, we show directly without. So the way Zinger proves that these numbers are invariants, he says, well, define BPS using Gromovwitten, then prove this equality. Then because Gromovwitten is invariant, this is an invariant. which of course the invariance of Gromovwitten numbers is a very deep statement. So we somewhat studied the question directly, and we also proved the finiteness part. Okay. Yeah. But a lot of, as I will show, a lot of ideas of what we do goes back to papers of Ionel and Zinger. So I will talk a little bit about this now. So right. So maybe I will talk about some ideas involved in the proof. So I will talk a little bit what goes into the proof, and then maybe I will try to say some speculations about what to do when your class is not primitive. So let's say we want to prove. Let's say we just want to prove this part. So maybe we want to show that for a primitive class, you can count the curves. This is an invariant, and moreover, this invariant vanishes for large genus. So that two parts, that this is an invariant, this number is invariant, and that it vanishes for large genus. So let's start with the first one. So A is primitive. How to define NAG. So that's the first part, maybe A. So of course you want to choose a generic J. You want to look at the space of these curves. And you want to say that this is a finite set. And you know that you can embed it in the modular space of stable maps. So the only thing you have to say, what is the closure of this set inside this big space? And this particular case is much easier than the general case, because you know that there are no multiple covers. So from the beginning, you rule out the biggest difficulty, because this class is primitive. And in general, if you want to say something about how this space interacts with multiple covers, you need to study this problem of superrigidity, because superrigidity is exactly what tells you how multiple covers interact with this component. But here, let's not worry about this. What can still happen is that you have bubbling. So you could have a sequence of curves, which so some maps, ui to x, which in the limit degenerates to a map from some kind of bubble tree. And you have to study when such a degeneration happens. So because we're in dimension 6, you can actually show that you can rule out most bubbles by index calculation. So for example, assume that there is only one bubble. Well, if there's only one bubble and both components are non-constant, then this is some non-constant holomorphic J-holomorphic map. This is some non-constant J-holomorphic map. You can show that both of them have index 0. Well, that means that generically they are, generically they are rigid. And if you have two rigid maps, because these are from dimension 2 and 2 plus 2 is smaller than 6, generically they will not intersect. So for example, a bubble which has one bubble component and both of these components are non-constant cannot generically happen. And you play this game and you use some combinatorics to see that actually most of these bubbles cannot occur. But there is one instant that you cannot simply rule out by index calculation, and these are these ghost maps. Because of course, ghost maps always exist, as I said at the beginning. So you could have say a sphere like that, and anything you want, it could be even a singular curve, and a map which is constant on this component and something non-constant on the bubble. So this entire component is sent to a point. And of course, maps like that always exist. So you have to study when such a map is a degeneration of embeddings. So in other words, you have to study the gluing problem. And this is something that in the genus 1 case was studied by Ionel and also by Zinger independently. And a lot of what we do is based on their ideas. So let's see. So you need to study gluing. What I mean by this, you start with this map, and you ask if you can deform it to a map from a domain which is a small smoothing of that domain. So let's say you have some kind of gluing parameter, maybe the radius of the circle epsilon, and you ask if for small epsilon you can deform this map to a map from such a domain, which is obtained by taking something which is constant here, something which is your map on the sphere here, smoothing it, and then perturbing, and using essentially the implicit functions here.
Did you erase a genus? My vision's not very good.
Yes, this is a it's a cartoon. Genus is G. Greater than greater than 0. So as I said, for genus 1, this is something that was studied by Ionel in her thesis and independently by Zinger. So what is the upshot? Well, anytime you do some kind of gluing, you will have a Kuranishi model for a neighborhood of the modular space of these things inside the modular space, the compactified modular space. So you need some sort of Kuranishi model. And in some oversimplifying a little bit, this will be given by a map. So you have some kind of space of infinitesimal deformations, space of infinitesimal obstructions, and also this gluing parameter. It's really a small complex number, but I can think of it just, there is some kind of rotational symmetry, so I can just think of a small real number. And the moduli space is locally given by the 0 set of this Kuranishi map. So I'm describing the local neighborhood of this curve in the moduli space. But now these deformations and obstructions are quite easy to understand in this special case, because you know that your map is actually constant here. So if you just forget about this, let's say that this map was unobstructed, rigid on this component, then you know what are deformations and obstructions of the constant map. So in fact, these will be just h0 of your, if this component is sigma, h0 sigma, just holomorphic functions on sigma, tensor, the tangent bundle of x. So let's say this map is constant. So let's say that this map sends this entire component to some point P in x. And if you just write down what are the deformations, they're just constant holomorphic functions, tensor the tangent space. So this, of course, just C. There's only yeah. And this guy is just the H1 of the same thing. Of the sheaf of holomorphic functions. So by third duality, this is actually the same as holomorphic one forms. So sections of the, what should I call it, canonical sheaf dual. And this map, actually, you can write down the first order expansion of this map. So how would I want to write it down? So let's say kappa has two arguments, epsilon, and some sort of vector. And what you can prove that this map, okay, this map is supposed to take values in the dual space of the space of holomorphic one-forms. That means that if I plug a holomorphic one-form, it should give me a number. So let's say I plug some holomorphic one-form. What do I call holomorphic one-forms? Eta. So eta is a holomorphic one-form on sigma. And I want to produce a number. So this number will be epsilon times you evaluate this holomorphic one-form at 0. So this point, let's call it 0. This is a point in the Riemann surface. And I can evaluate the holomorphic one-form that gives me a number, complex number. And then what do I do? Let's see. So I guess I should take holomorphic one-form tensor TPX. So I have holomorphic one-form tensor, some other vector, and that will be this times you take an inner product of V and the derivative of the bubble map at 0, say. So I have two components. I have this ghost component and the point 0 here. That corresponds to a point in P1, which I also call 0. And this map is the bubble map. So on this component, the map is constant. And on this component, it's some non-constant map, which I call B. And what you do, you take the derivative of this and evaluate it at 0. And then there are some higher order terms. So O of epsilon square and O of V. OK, so what does it tell me? If the genus is greater than 1, at any point, there exists a holomorphic one-form which does not vanish at that point. So I can always find a holomorphic form for which this is non-zero. And if the derivative of my bubble is also non-zero, then this leading term, so if the derivative is also non-zero, then this guy is always something like c times epsilon, which means that its only 0 is at epsilon equal to 0, which means that I can never smooth it to epsilon greater than 0. So that means that if I have a bubble such that this is an embedded curve, and I attach some constant component, I can never smooth it. Or if you reverse the entire reasoning, that tells you that if you have a map like this, which is a limit of embeddings, then the bubble has to have a cusp. Has to have some kind of singularity at this point. And I think this is a very interesting result, which goes back to, as I said, Einstein and Singer, which I think it would be nice to prove it without using all this gluing theory. It would be nice to just prove it directly studying limits of maps or limits of currents, that if you have a sequence of embedded higher genus curves and in the limit you get the image which is of lower genus, then at this point where you contracted the genus, that has to be a singular point. But I don't know how to prove it without using all this gluing theory. So I wanted to advertise this problem. And this is related to a problem stated by Rouen a long time ago, namely, is there an analog of an arithmetic genus for J-holomorphic curves? So for genuine holomorphic curves, you would say, well, this guy has, there's some kind of semi-continuity of the arithmetic genus, even though I lose geometric genus. But I think it's an interesting question to try to answer also in the almost complex set. So that's how you rule out the bubbles. And moreover, this also works in one-dimensional family, because the condition for this to be a non-embedded curve is of codimension 2. So that means if you vary J, everything is the same. So actually, this set is compact for a generic J. And moreover, it remains compact if you vary J in a one-parameter family. And so that essentially proves that this number is invariant. So now how do we prove that there are only finitely many of these curves if the genus is allowed to go to infinity? And as I said, this is essentially This follows from some ideas that were used by Taubes in dimension 4 and from regularity theorems for J-holomorphic currents. So now the second part, B, why does it vanish for a large genus? Well, so now you have to assume that there are infinitely many curves, and you want to arrive at a contradiction. So assume that there are infinitely many curves, say C1, C2 in X. They're all J-holomorphic or all in the same homology class, but their genus possibly goes to infinity. If that happens, then you have no hope of extracting any information from Gromov's theory of J-holomorphic maps, because these are maps from different domains. But you can still take a limit as currents, essentially because the area of these currents, these are all minimizing, and the area of these currents is bounded. And then there is a theorem. So actually in this, so there is a theorem of Rivière and Tian. But actually, we need a version which appears in the Lelis and Spadaro and Spoloar, which says that, in fact, this current, which a priori could be some horrible, very singular object, that C infinity is actually the image of a J-holomorphic map. And because we are allowed to choose J generic, the worst that can happen is that this is actually just multiple cover of an embedding. So it's actually a very nice. So it's actually an embedded J-holomorphic curve in this case. So we don't have yet a contradiction, but to get a contradiction, you have to take a second limit. So to speak, you have to expand. Now you have some kind of limiting curve, and in some sense, you want to expand all these CI, in some sense, in the Taylor series around C infinity. So for I large, because the convergence of currents implies in particular convergence as sets in the Hausdorff distance, and this curve is embedded, so it has some normal tubular neighborhood. Let's call it N. So this is a normal bundle. And for I large, all these other curves must lie in the tubular neighborhood of C infinity. And as I goes to infinity, they get closer and closer. That's what the convergence of currents implies. So if you want to extract more information, what you can do, you can rescale. So set Ci tilde to be epsilon I inverse times Ci. So I choose a sequence of numbers epsilon I, and because now I'm in the normal bundle, I can start rescaling in the normal direction. And I can rescale in such a way that the Hausdorff distance of Ci tilde and C infinity is 1. Now, these rescaled Ci's are not J-holomorphic, because in general, my J, is not scale invariant. But you can take the sequence of Ji, which are rescaled versions of J, and what you can show that this actually converges to an almost complex structure on N. Great. So now I play the same game. These guys are maybe, they are Ji holomorphic. You can prove that they satisfy an area bound. Therefore, you can extract the limit as currents. And using these results, this current that you get is again an image of a J holomorphic map. So these rescaled guys converge to C infinity twiddle, which is some sort of J infinity holomorphic curve inside N. So you get some curve. C infinity twiddle. And moreover, this curve is different from the 0 section because I assume this condition. Great. Well, this curve can potentially have many components, but what you have to show, what you have to show, and this is essentially a topological condition, that one of these components, so what else to say? So what you want to show is actually there's one component on this infinity such that the projection, there is a projection map, and the point is that this projection map is J infinity holomorphic. And what you have to show is that there is one component of this infinity such that the projection is actually a biholomorphism from that component to the 0 section. And after you do that, you're done. So let me say, so there's a component, there's essentially a topological argument of C infinity twiddle, which projects biholomorphically, isomorphically, to C infinity. And that is essentially a contradiction. Why? Because this C infinity, so you can show that J infinity holomorphic curves in the normal bundle are essentially the same as solutions to, maybe I'll write it like that, J holomorphic normal vector fields on C infinity. So essentially, these are the things that give you a deformation of C infinity inside your original manifold. But generically, all J holomorphic curves are embedded and rigid. So generically, the C infinity cannot have such a normal vector field, and that's a contradiction. This is a contradiction. The contradiction, of course, follows from the fact that we assume that we have this limit, this sequence. And you can already see that the same argument can be used also to consider a situation in which this fails, because even if there is no component which maps isomorphically to C infinity, because the projection map is holomorphic, what you get essentially is a multi-valued graph, graph of a multi-valued section of the normal bundle. So that's something that corresponds to infinitesimal deformations of multiple covers, and this is, of course, what superrigidity deals with. So you can already see how the general proof in case 1 also works, assuming that a generic almost complex structure is superrigid. So maybe let me just.
Am I missing something? Why the lack of deformations actually imply a contradiction here?
Because I extracted this component. So that means that this component is a graph of a J holomorphic normal vector field. And having such a normal vector field, if you can, is the same as having an infinitesimal deformation. So this line is something that you have to prove, that there is a one-to-one correspondence between curves which are holomorphic with respect to this J infinity and these vector fields. That's something we learned from a paper of Taub's.
So did you just make a comment about the case where C infinity tilde is branched?
Yeah. Then essentially what you get is not a normal vector field, but a multi-valued normal vector field. Okay. And superrigidity essentially says that there exists no such multi-valued vector fields. Yeah, thank you. Well, okay, let me just finish by saying that, so we learned what the BPS invariant is for primitive classes. It's just a naive count of curves. The naive curve counting for classes that are not primitive is most likely not going to produce an invariant, but there is a conjecture that you can put weights, you can count holomorphic curves with weights in such a way that will produce an invariant. And would I expect that in this way you could define a symplectic analog of the Donaldson-Thomas invariant in algebraic geometry. But let me finish there. So thank you.